Just take a look around you right now. I'll bet you can spot at least a dozen things made of plastic without even really trying. Your phone case, the keyboard, that water bottle on your desk, they're everywhere. So common we barely even see them anymore. But behind every single one of those simple objects is this hidden world of super complex science and, honestly, pretty counterintuitive engineering. And that's exactly what we're going to get into.
Would you believe that every single plastic thing you own, no matter how complex the shape, started its life as just a handful of these little pellets? Seriously, the journey from this raw stuff into a finished product that actually works, well, it's this incredible engineering puzzle, full of challenges you probably never even think of.
And that journey from the simple pellet to the final product, it brings us right to what I like to call the plastic paradox.
Just let that sink in for a second. We've been working with wood and metal for thousands of years, right? We have a gut feeling and instinct for how they'll behave. But modern plastics? They've only really been around for a couple of generations. Our intuition about how they bend, how they cool, how they break, it's almost always wrong. And that is why good design isn't just a nice-to-have, it is absolutely crucial.
So, where does all this complexity even begin? Well, the first layer is just the mind-boggling variety of materials to choose from. 50,000. Yeah, you heard that right. That's roughly how many different grades of plastic a designer has to choose from today. Can you imagine being faced with 50,000 choices before you've even drawn a single line? Just picking the right one with the exact right properties for the job is a massive challenge all by itself.
So to make any sense of those 50,000 options, designers start by sorting them into big families. You've got your thermoplastics, which you can melt down and reshape over and over, kind of like butter. Then you have thermosets, which, once they're heated and set, that's it. It's a one-way trip. Think of it more like baking a cake. And even within those groups, you've got more divisions, like amorphous versus semi-crystalline, and that affects everything from how clear it is to how strong it is. It's a dizzying world to navigate.
Okay, so with all this complexity, how do designers possibly get it right? Well, a lot of the time, it all comes down to one single fundamental principle. You could basically call it the golden rule of plastic design.
And it's a perfectly fair question, right? Our intuition, the one we've built up from wood and metal, tells us that thicker equals stronger. So why not just make a big, solid, chunky plastic part to make it super durable?
Because this happens. Look at this. The picture on the left, that's the perfect part. How it was designed in the computer. The one on the right is what actually comes out of the machine. It's warped, it's distorted, it has these ugly dents called sink marks. And the reason is simple. Plastic is a terrible conductor of heat. So when a thick part cools, the outside gets hard first while the inside is still basically liquid. As that molten core finally cools and shrinks, it pulls the solid surface in on itself, creating all those flaws. So the solution, and this is just brilliant, is totally counterintuitive. You don't design a solid block, you design a hollow shell. By coring out the part, as they call it, you create these thin, uniform walls. That means the whole piece can cool down and shrink at the same rate, and you get a strong, stable, perfect product. And you even use less material doing it. It's a total win-win. Now, to pull this off, designers follow a few key guidelines. The big one, number one, is to keep that wall thickness as uniform as you possibly can. We're talking about a sweet spot usually between 0.5 millimeter and 5 millimeters, depending on the material. And if you absolutely positively have to change thickness, you have to do it very, very carefully. A sudden sharp step from thick to thin is just a recipe for disaster. It basically creates a weak point and makes the cooling even more uneven. So instead, what good design does is use a gentle, gradual transition, like a smooth ramp or a curve. This lets the melted plastic flow nicely and helps the part cool down evenly, avoiding all those internal stresses that could cause it to just crack and fail down the road.
All right, let's look at a perfect example of these principles in action. It's something you've probably used 1,000 times and never given a second thought. The snap fit.
Seriously, think about the battery cover on your TV remote. That little clip that clicks into place? That's a snap fit. And it's an incredibly elegant piece of engineering. It gets rid of screws and glue and all these extra parts. It's molded right into the main component, which makes putting things together super fast, super cheap, and super simple. It is pure design genius. So to really get how a snap fit works, you have to understand this one key concept: strain. Put simply, strain is just how much a material can stretch or bend before it either snaps or gets permanently stuck in that bent shape. For a snap fit to work, it has to bend just enough to click into place and then spring right back to its original shape, all without going past its strain limit. And this picture shows you exactly how designers manage that. On the left, that's the simple, obvious way to design it, just a straight beam. But when it bends, all the force, all the stress, shown here in red,
It all gets focused on that one single point at the base. It's a huge weak spot, just waiting to break. Now, look at the design on the right. By tapering the beam, the stress gets spread out much more evenly along its whole length. This simple change makes the clip way stronger and more durable so it can snap and unsnap thousands of times without ever failing.
So what's the big takeaway from all this? Well, it's that the most important parts of design are often the ones you can't even see.
Good plastic design is really an invisible science. It's this whole world that's governed by rules that go completely against our common sense. A world where making something hollow actually makes it stronger, and where the shape of one tiny little clip is dictated by all these complex calculations about stress and strain.
So the next time you pick up any plastic object, just take a closer look. See if you can spot the uniform walls, the smooth, rounded corners, the clever little clips. It might just make you wonder what other invisible designs are hiding in plain sight in all the things you use every single day.